Allora, innanzitutto grazie a tutti per essere venuti e anche ringrazio le persone che sono collegate in streaming. E quindi oggi questo è un ciclo di seminari che appartiene ai Breakthroughs in Material Science ed è organizzato dal nostro dipartimento. E oggi abbiamo come ospite il professor Stefan Kaskel. So, I would like now to go on in English. So, Professor Stefan Kaskel is a full professor at the University of Dresden, and he's got his PhD degree at the University of Tübingen, and then also his habilitation in inorganic chemistry, and he worked at the Max Planck Institute and the University of Bochum with Professor Roland Fischer. So he has been Dean of Faculty of Chemistry and Food Chemistry in Dresden. He was also head of business unit in Fraunhofer Institute in Dresden, and then a group leader at the Max Planck Institute. So he has received 2 ERC grants as an advanced grants, so congratulations for these achievements. And he has been a highly cited researcher. He's still a highly cited researcher from my Climate Analytics. So he has been editorial board member, and he has supervised students, postdocs, so many, high number of students. And his activities is mainly focused on study of metal organic frameworks, and especially there are the new metal organic frameworks called DUT, that means Dresden University of Technology. So they are well known in all the world, and there are many groups in the world that are studying these DUT metal organic frameworks. But his interests are also wider because he's interested in energy materials for sustainable energy supply storage. So he's also interested, he's working in the field of environmental materials and the design and coating of nanostructure surfaces. And he has published 800 publications. And so the number of citations is about 60,000. And so now today his lecture is titled Responsive Frameworks, Serendipity or Rational Design. But I want also to emphasize that he was one of a pioneer researcher in the field of flexible metal organic frameworks. And so there are many special characterization techniques that he has applied, he's still applying in order to characterize these materials. So.
Yeah, I take this one. Yeah, thank you, Angelina. Welcome, everybody. Thank you for the great hospitality. It's really a great honor to be here in Milano at this famous university, and also I see a lot of very interesting activities here in the field of metal organic frameworks. My group has a lot of research interest in different areas. We work a lot in the area of porous materials for various kinds of applications. You can use porous materials for energy applications, for energy storage, for example, in supercapacitors for ion storage, but also in batteries. Especially in lithium-sulfur batteries. Porous materials can be used to store a lot of sulfur. So these are many applications. But one of the interests, of course, is also that you can use porous materials as catalysts or for gas storage and for the separation application. My group is very much focused on synthesis of porous materials. We develop highly porous materials, metal organic frameworks, which I will talk about in a minute. But then also the emerging class of the covalent organic frameworks are very interesting materials. These can be also considered as two-dimensional materials, so they have interesting surface properties. And then we should also not forget that there's the old class of carbon materials. Carbon is a very stable type of material. You can also generate very high surface areas, up to 3,000 square meters per gram. And these materials are especially valuable in battery applications because they have electrical conductivity. And this is also some of the work that we are doing. So, there are so many fields that you can explore with advanced materials for the future. I think this is really the beauty of our field. And today, I will mainly focus on the metal organic frameworks because this is also a research topic which is very much studied here. We can consider metal organic frameworks as polymers, as we have discussed yesterday. But of course, they are crystalline polymers, coordination polymers. And forgive me for this little propaganda here, but I edited this book by Wiley in 2016. It's probably now the time to write a new book or edit a new book. So maybe you can help me if you are interested to write a chapter. I think we should also start a new book project. But the beauty of metal organic frameworks is really that they are modular materials and they profit from the organic chemistry because we can integrate modular organic building blocks. Often these carboxylic acids are used as very simple building blocks, bifunctional or trifunctional linkers that can coordinate to the inorganic unit. But the beauty is also that this brings people together, polymer chemists, crystallographers, organic chemists, but also inorganic chemists. Inorganic chemists know a lot about coordination chemistry, and we can use different kind of subunits, which we can call clusters, or in coordination chemistry, you would call them multinuclear nodes, basically, which have the role to connect these linkers together into three-dimensional structures. And here are some of the pioneers in this field who also contributed to this book: Omar Yagi, Gérard Ferré, Susumu Kitagawa, but there are many more pioneers in this field who pioneered the field of metal organic frameworks. Omar Yagi with the MOF5 was the first structure, of course, which produced a material with very high specific surface area, 3,000 square meters per gram. I mean, if you buy an apartment or rent an apartment in Milano, then 3,000 square meters would be really something very, very expensive. But we can make this basically in 1 gram of material. And maybe it's difficult to live in a MOF, but at least we have a very high specific surface area. That was also the motivation, and Angelina also said already that we call our metal organic frameworks DOT. This is the local patriotism that all the MOF people have, basically, that they name the materials after their institution for Dresden University of Technology. And for a long time, one of our main interests was really to develop very highly porous metal organic frameworks with huge porosity for gas storage applications. You can store gases like hydrogen or methane, natural gas, or CO2 in the pores. And it was also curiosity driven. We wanted to ask the question, what is the highest surface area that we can achieve? And these are some of the materials. I will come to that later also. Which have record porosities, 6,000 or even 7,800 square meters per gram. And this is the material DOT60, which currently still is the world record in terms of porosity. And this also creates debates, of course. Is the BET theory still valid? We have here some experts in how you calculate these surface areas. But if you don't believe in surface areas, there's also the pore volume. And the specific pore volume here is 5 milliliters, 5 cubic centimeters per gram. And this is 1 order of magnitude higher than a traditional porous material, like a zeolite, for example, or an activated carbon, which typically can reach 0.2, 0.5 cubic centimeters per gram. So these materials are really record type of materials. But today I would like to take a little bit a different turn, and I would like to tell you about a story that began for us in 2008, very early on. At that time, I started my career, by the way, in a very old building. That was from 1923. And at that time, we were still in this very old building with very little instrumentation. And then suddenly this PhD student, Michael Sabo, came to my lab and said, "Stefan, I found something very strange. I have here a new MOF, a new compound. I don't know the structure, But when I put it in liquid nitrogen, it changes the color. So the upper part of the sample, which is still warm, is yellow. And here the colors are maybe a bit difficult to see, but here at this low temperature, it is green. And it was totally strange. At that time, we could not do X-ray diffraction at these low temperatures, and we did not understand anything. But it was this observation that triggered basically a lot of new studies on this kind of material. And only later, when we started the first experiments where we put these crystals in a microscope and then exposed them to a solvent, we realized what these crystals are doing, what these structures and materials are doing, basically. So here you see the same MOF, we call it DOT8, basically. And after the evacuation, it forms a closed crystal. This is the closed crystal, basically. And then when the solvent is coming, basically, it shows a huge expansion. So these materials are dynamic materials. So they change their structure depending what's inside. So it's similar to us. I mean, we eat something, we drink something, we change our shape, we change our size, we grow, we shrink. And somehow these materials are adaptive. They change their structure. They are responsive to something. They are responsive to a gas or a molecular stimulus in the end. And this triggered a lot of developments for us, basically, because now you have a new task. It's not like static analysis that you normally do as a chemist, basically, that you make a material and then you put it on the bench and you analyze it, you do X-ray and NMR and whatever. But now you have a material which is dynamic, so that you need to monitor it during the transformations, when it takes up some gas or when it releases gas, to get a better understanding what is going on, what is happening there. And over the recent decades, many people, us, but also other people, have developed advanced techniques that allow to monitor the structural changes and also the state of the gas and the molecules inside the pores of these materials with what we call in situ methodologies. And it means basically that you run NMR, but at the same time you dose a gas to the sample, you adjust a certain pressure, and you monitor how the material, how this responsive material responds basically to the outer stimulus. And over the years, EPR spectroscopy, NMR spectroscopy, but also many diffraction methods, these materials are crystalline, so X-ray diffraction is an enormously powerful tool basically to analyze these materials, and of course also other spectroscopies were developed more in depth in the last centuries. So just to give you an overview, we developed some methods for the synchrotron, especially X-ray diffraction methods, and also other authors, of course, developed similar methods, but the specialty for us is that we have basically a special dome architecture where the sample is located in the beam, and then you can dose a gas to it. You can measure a full gas absorption isotherm to the sample. You can also expose your sample to vapors and measure the X-ray diffraction patterns, powder diffraction patterns. We also developed experimentation for high-pressure gas absorption. And in recent years, we also developed multi-stimulus approaches, so that's also quite interesting. Some people are interested in dosing a gas, but then at the same time also inducing a stimulus by an optical stimulus, by UV light, for example, or visible light. And this is also, these instrumentations we have developed over the last decades, and they are now available at the KMC2 beamline at the Bessie synchrotron. Of course, traveling to a synchrotron is always quite expensive and takes time, and it's difficult to get measurement time. Therefore, we also developed this as a diffractometer in our laboratory. This is a commercial panalytical diffractometer where we adapted our in situ methodology. Here you see the beryllium dome, basically, which is X-ray transparent, and this can operate at very low temperature, down to 30 Kelvin, and also a pressure up to 1 bar. And it can be used for non-corrosive gases. And this is really a working horse nowadays, because here you can measure a full adsorption isotherm on your sample. This is an enabling tool, and at the same time you can measure the powder XRD patterns that allow you to analyze what is going on in the structure. So, what is this magic material DOT8? It's a very simple architecture. It consists of a pedal wheel. We found this out by single crystal X-ray diffraction measurements. This is a binuclear complex, which is often called pedal wheel in the MOF field. And these are connected to 4 carboxylates, basically. And the carboxylate in this case is a naphthalene dicarboxylate. So initially you form these 4 rings. This is very similar to constructing a building. First, you basically have like square grids to form the different stories, and then you also need a pillar, and the pillar in this case is the small molecule DAPCO. And this is this material which shows a huge volume change. First, when you synthesize it, it has the open pore structure, but then when you desolvate it, when you pull vacuum basically, it transforms into a contracted porous phase. And you will see in the following a lot of these so-called adsorption isotherms where we record the uptake of nitrogen. This is the uptake of nitrogen on the Y scale versus the pressure. We record the pressure as a function of reduced pressure. P0 is the saturation pressure of the gas. So in this case, it's just the scale 1 bar basically here. And you see that this is a very particular isotherm. We call this the gating isotherm. This material basically is closed up to a certain gate pressure, but then at a certain pressure, suddenly it plops open basically and shows a huge uptake up to 30 millimole per gram. So this would correspond to 2,000 square meters per gram surface area. So this material is a typical responsive gating type of material that we discovered here. And what is also very typical for this switching behavior, this opening and the closing, is that you see a hysteresis in these adsorption isotherms. Whenever you see a hysteresis, it means that your material is flexible, it's responsive, it changes the structure. The adsorption, the uptake curve is different in this case compared to the desorption curve. And this shows basically the responsibility of this type of material. Here you see also a little bit what this means for the structure in detail. So in the large pore structure, we have a very regular tetragonal binuclear complex, the pedal wheel, ideal pedal wheel structure. But in the contracted phase, so the driving force for the contraction is basically are the van der Waals forces between the naphthalene rings. This is the driving force. But in this contracted structure, the pedal wheel is quite distorted. And you see this here also, that the x-axis, the axis between the nickel atoms, is a bit off. And this also induces this color change. You have different colors for the closed pore and for the open pore form. And this material shows the huge volume change. The unit cell volume changes by more than 200%. This is a record in the field of flexible metal organic frameworks, and this is a typical characteristic. Now, this deformation of the cluster is also a first signature that you can use for in situ spectroscopy. And I want to give here one example from EPR spectroscopy without going too much into the details. But EPR spectroscopy monitors the spin of a metal, essentially. And the beauty of this structure is that you can substitute some of the nickel atoms by cobalt. Here only 2% cobalt was substituted. And the cobalt has S1/2 signal, basically, which is coupling with the nucleus, the nuclear spin of the cobalt, and therefore gives a characteristic hyperfine spectrum in the EPR spectrum. So you can see this here, many, many lines, basically. What you can do now is basically you can, together with the group in Leipzig, Andreas Pöppel, we developed basically a setup where you can dose gas to the MOF and then monitor the EPR spectra, and you see that this symmetrical spin structure, basically the signal with the multiplet structure, comes up at a very defined pressure, here at about 40 millibar basically, and then this is only for the adsorption branch, stays constant, and you can integrate this signal and then follow the adsorption branch and also the desorption branch, and in this way you get some microscopic insights basically in the structural transformation. When it's contracted, there's no signal because there's some asymmetry and the signal is not detected, but then when it opens up basically you can see that this signature follows very much the adsorption isotherm of this kind of material. Now, for a long time, we were very much struggling with the real and detailed structure of this kind of material. When Michael Sabo came for the first time to my laboratory with the single crystal structure, he said, this looks really ugly. He came up with pictures which looked like this. So it seems that the naphthalene ring looks totally disordered. And you can see this also in the single crystal X-ray data. There are lots of streaks here, multiplets, multiple peaks basically here. This doesn't look like a good single crystal structure. And many people then say, this is also typical for science, then it's not a good structure, let's not look at it more in detail, or let's ignore it basically. But this bothered us very much for a long time, and we were very much suspicious what is going on there. And for this, it was very important for us a cooperation with Andrew Goodwin in Oxford. And we realized more in detail that the problem here is that the naphthalene dicarboxylate linker is not a linear linker. It has a very small but distinct step function, 1.2 angstrom basically. It's like a stair if you're going up basically. Yeah? And you know, if you have stairs that can go up, then there are also stairs that can go down. And this creates a lot of chaos or disorder in this kind of structure. So you can have different kind of nodes where all the linkers are step up, or all the linkers are alternating, step down, step up, step up, step down. And in order to rationalize this, Andrew Goodwin in Oxford helped us to rationalize this in this kind of staircase architecture. So you can rationalize the structure, the disorder in the structure basically by identifying structure motifs that are down, down, up, up. Or there are also structural motifs, rings, circles that are down, up, down, up. So here it's alternating basically. These are alternating rings. And we symbolize these rings as tiles which are gray. It's like a puzzle. You know? It's a bit like a puzzling. I think we talked about the children education where puzzling, and scientists are also children in a sense, and like the puzzle. So we identified different kind of pieces for the puzzle. These kind of pieces and then these kind of pieces where you have basically up, up, down, down, and they can have different orientations. And now the children would be able to make different kinds of structures with these tiles basically. And this is also what you find in this structure here. You can either have only one kind of tile, for example, this blue one, or you can only have gray tiles that constitute a structure, or you can have wild mixtures, basically, or you can have a mixture of gray and yellow and green tiles, which make the structure very complicated. So, which structure is the real structure of our moth? We were quite suspicious and to analyze that. We analyzed this very much in detail, and what we found is that the guest, the molecule inside the pore of the structure, defines which kind of disorder we have. So you can have different kinds of tile combinations depending if you have more a polar solvent like DCM, for example, or if you have a polar non-protic solvent like NMP, you have more this kind of tile structure. So we were very surprised that the solvent basically determines what kind of disorder structure is forming here. And you can imagine that this creates a lot of problems for a PhD student. If you solvate your compound and your material in this solvent or another solvent, you always get a different structure, so that's very confusing. So these peaks here are very distinct basically for these subtle structural changes. And we were even more surprised to find out that after the synthesis, when you exchange the solvent, you can reversibly transform the structure basically from this more disordered structure to a more tetragonal disordered structure to a monoclinic and a more tetragonal structure. So you can even switch reversibly in between these different types of disordered states basically with the solvent. So this took us a long time, and maybe this is also an interesting take-home message. Sometimes it's worth digging deeper to find out what is really happening in this kind of structure. Now, let's look a little bit more closer at the contracted phases. I told you that the nickel cluster is very much distorted, but the distortion is even more heavy when you go to the cobalt and to the zinc cluster. So in the contracted structure of the zinc variant, so you can make all the DOT8 structures with nickel, cobalt, zinc, and copper. In the zinc structure, you almost go from a, let's say, square pyramidal coordination to a more tetrahedral type of coordination, and also the distance between the zinc atoms is very much changed. So this already tells you that the node here is the flexible unit. So the zinc cluster is very flexible. It's a soft node, while the nickel cluster is more a hard node. It's more difficult to transform. I will not talk about the copper structure because it's a bit more complicated. It's different. And this you see also in the energetics. When you calculate the energy difference between the open pore structure and the contracted pore structure, you see that the energy difference is the smallest for the nickel, but the largest for the zinc. That means for the zinc structure, the closed pore structure is the most stable one, actually, compared to the nickel, because the nickel is more a harder spring. It tries to reopen the structure. It pushes the structure open again. And now we can understand how we come to functions also in these kind of materials, because now we see selectivity. Because the energy difference is the smallest for the nickel, when you do nitrogen adsorption, when you look at the nitrogen uptake, only the nitrogen can open only the nickel morph. But the other morphs, cobalt and zinc, the energy difference is too high. Nitrogen has not enough energy to compensate these energy differences, and therefore the other materials stay closed. When you use a more powerful adsorbent, a molecule which can push the pores open because it's solvating the inner part of the structure, so the DCM is a more powerful solvent because it has stronger interaction with the pore walls, then you can see this subtle interaction much better. So the DCM can easily open the nickel morph, but for example, for the cobalt morph, you need higher energy, you need higher pressure basically, higher saturation pressure basically to open it, and you can also not open it completely. You don't reach the same saturation. And then for the zinc, because the energy difference is even higher, it is even more difficult to open the zinc structure. So this allows you now to rationalize also with this model system how responsivity works. So the zinc cluster, the metal cluster really regulates the selectivity in this case. And then you can also introduce selectivity. If you have a morph which is not so easy to open, like the cobalt morph compared to the nickel DOT8, the nickel DOT8 would open for dichloromethane, trichloromethane, and tetrachloromethane. But the cobalt morph, because it's more difficult to open, it only opens for the dichloromethane, but trichloromethane and tetrachloromethane are not able to open the morph. So this allows you also to introduce selectivity with the responsivity of the metal organic framework. Now, one very strange phenomenon for these responsive metal organic frameworks is the importance of size effects. We all know that when we go to the nano regime, everything is different. And this can become very complicated in this class of materials. And what we found, and there's also, of course, other work by Susumu Kitagawa on different systems, but what is a very important finding is if you make your material, the DOT8 nickel, for example, as nanoparticle, then the responsivity is completely lost. So there's no hysteresis anymore. the material is open all the time. It does not close anymore. And we call this a type 1 isotherm here for nitrogen adsorption. Only if you have large crystals which are flexible, then you see the flexibility and the hysteresis in the isotherm. This gives you also another way to tailor the properties of these kind of materials, but it's very important to keep this in mind, because when you tailor the cluster, you always need to compare also similar crystallite size, and this is another dimension to tailor the properties of these systems. And this is very important for the selective separation of gases. For example, CO2 separation is an important topic for environmental applications, and also the separation of CO2 from methane is an important industrial separation. When you want to basically have a pure natural gas, you want to have an adsorbent which selectively takes up the CO2. And this is very interesting when you compare these nanoparticles with the flexible DOT8. You see that, the nanoparticles have some selectivity for CO2, so they take up CO2 more easily and more CO2 than compared to the methane, because the interaction with the CO2 is higher. But for the flexible MOF, this is completely different. The selectivity is much, much higher, because only the CO2 can open the pores, while the methane cannot open the pores at all. So for methane, the gas is not strong enough to open the pores, and therefore the uptake for methane is very little for this material. So you have a huge gain in selectivity, and you see this also not only for the pure gases, but also for the one-to-one mixtures. Basically, when you compare the selectivity, you have in the mixture, in a one-to-one mixture, you have CO2 and methane entering the rigid DOT8, because it's rigid all the time. But the flexible system basically only takes up the CO2. Almost the total gas that is taken up is only CO2, while the methane is not taken up. So this is a very special character of the flexible MOFs. Almost like enzymes, they are responsive to a certain type of molecule and open their pores only for a certain molecule. Yeah? It's like when you are at home, you only open the door for your guests that you want to have inside, right? While other people that you don't like or that are not familiar to you, you don't let in. And this you can use also here in this type of flexible materials. Again, here also we explored some in situ methodology in cooperation with my colleague Eike Brunner, where we used in situ NMR spectroscopy, because you can use 13C enriched CO2 and 13C enriched methane to study the selectivity and the selective uptake of these gases. We developed a special cell for static NMR measurements, and here you see basically the NMR measurements of the adsorption curve, basically. And what is very characteristic when you adsorb a mixture of CO2 and methane, here it was 2-to-1 basically, then you see that only the CO2 goes inside the pores. And what is very characteristic for the NMR spectra, for static NMR spectra, is that when the molecule is mobile, here this is the methane signal, this is the CO2 gas phase signal. When the molecule is mobile, you get a very sharp peak. But once your molecule enters the pores, it is restricted in mobility. And in a static NMR experiment, then you get a very broad peak, which is called a tensorial signal. And this has a very characteristic signature for the adsorbed species. And this allows you to distinguish between the adsorbed species, which is this broad signal, and the mobile species in the gas phase. So you can basically quantify the gas phase and the adsorbed species at the same time. And you can basically quantify the adsorption isotherm also from the integration of the NMR signal. And you see that there's a pure uptake of CO2. There's no uptake of methane gas, given the detection limits of the NMR spectroscopy. So the flat for the curve for methane is totally flat. Normally you would expect the methane to be here, basically, but we only see it in the gas phase. So it is only selectively the CO2 that is taken up, as proven by this in situ experiment. But there are also other separations that become more interesting recently. For example, the isotope separation is a very hot topic recently. The separation of deuterium, tritium, and hydrogen, basically. Also, water isotopologues, there are many studies in this direction. And we were very surprised to see that this MOF selectively opens its pores for deuterium, while hydrogen is excluded from the pores. And this is an experiment which we did at about 20 Kelvin. So you see the pores, they have a huge uptake. 35 millimole per gram is really a lot at 23 Kelvin. And you see the characteristic hysteresis, while the hydrogen shows no uptake at all. These are the single component isotherms. And in a mixture experiment with the 1-to-1 mixture in cooperation with Michael Hirscher in Stuttgart, we measured a selectivity value up to 11. So that's also quite good selectivity at these high loadings. And again, with the in situ methodologies, you can also analyze now where are the D2 molecules inside the pores. And you can do this with neutron powder diffraction. It's very powerful. You see the different powder diffraction patterns with deuterium. You can localize the deuterium molecules and then also get an insight into the structure of the adsorbate inside the pores. So I hope I could show you that these are very interesting materials, and there are still many open questions in this class of gate-responsive gating metal organic frameworks. If you're interested, we just published a review on these kind of materials. And I think there are still many open questions also that need to be studied. But before I close, I also wanted to tell you about a different story, which was also maybe a combination of serendipity and rational design. And this was a structure that we discovered in 2012. We call this material DOT49. At that time, it was also a very highly porous material. 5,300 square meters per gram. It's even higher than the material form of 5 from Omayagi. And this is also a very neat architecture. It's a very simple architecture in a sense. Here we are using a bent carboxylate, a carbazole type of carboxylate, which forms a polyhedron. We call these polyhedra MOP. So they have 6 pedal wheels. It's the same pedal wheel unit that you saw before, but now it's copper, not nickel inside, copper 2+. And we form these metal organic polyhedra. And the student Uli Stöck had the idea to connect these polyhedra with a biphenyl strut, basically, to make this very porous structure, which has octahedral cavities and also tetrahedral cavities. So you have the MOP, which is porous, but then you have also huge pores, which are mesoporous, 2.4 nanometer, 1.7 nanometer. And it looks a bit complicated, but this structure is very familiar to all the chemists and material science because it resembles the copper metal structure. I think you're all familiar with the CCP metal structure of copper. It's a closed cubic packing. We also call it face-centered cubic, a very simple structure. Essentially, here you see some of the models, basically, ABC, copper type structure. And many inorganic chemists like to use the metal of the model of the closed packings, basically, to also explain other structures like oxide structures. Because in between the metal spheres we have holes, which are tetrahedral and octahedral holes, and oxygen can go inside, or nitrogen, or hydrogen, and so on. And this is the same architecture, so cubic symmetry, basically. But now the metal atoms are substituted by these MOPs, and the octahedral holes are not 1 or 3 angstrom in diameter, but they are 24 angstrom in diameter, and the tetrahedral holes are 17 angstrom in diameter. So they're huge, and a lot of molecules can fit inside. So originally we studied this material more than a decade ago for natural gas storage applications. At that time, BASF was very interested to store natural gas for cars, and this material at that time was a record leader with a very high total uptake at 110, 120 bar. We could take up almost 0.5 gram per gram methane, so a huge methane uptake, basically at room temperature, so a very good material for methane storage. And that was very interesting for applications. But we were also interested to get a deeper understanding why this material is a record leader, why it is so special, why it can take up so much methane. And therefore, we started to record methane adsorption isotherms at the boiling point of methane, 111 Kelvin. And then for the first time, we saw a very strange adsorption isotherm. So this material takes up a huge amount of gas. We are here at 70 millimole per gram. But when you adsorb the gas, when you start to put some gas inside, here you see a very strange step. So there's a negative step in the adsorption isotherm. And then it's recovering. There's a big uptake again, and then there's a desorption step. But this negative step was very counterintuitive. It was more than 165 cubic centimeters per gram, 7 millimole per gram. So this means that the material pushes out gas, basically, while you are increasing the pressure. And this was very counterintuitive at that time, because from thermodynamics, it's forbidden, actually. When you increase the pressure, you should always take up more gas. You should not push it out. Yeah? That's totally counterintuitive. And many people also, when I gave presentations to the audience in the first time, then people said, oh, maybe your instrument is not good and you should repeat this measurement. Did you use a quantachrome? No, you should use a Bell instrument. And then in the other presentation, they said, oh, did you use a Bell instrument? Oh, no, you should use a quantachrome instrument. Or the other way around. And but no, we repeated this several times. It's absolutely reproducible. There's a desorption step in the adsorption branch. And this was a quite new phenomenon. So what is so strange here? Normally, when you dose a pressure to your porous material, you will always see that the pressure is decreasing because the porous material is taking up the gas. But in this material, when you dose a pressure to the cell, first the pressure is decreasing, but then it's pushing out gas. It's almost like these mushrooms which are exploding when you step on them. So they push out gas, and this was a quite strange phenomenon. Now you may say, okay, 111 Kelvin, that's exotic. Who cares? I mean, that's not for applications. I will show you that this also happens at room temperature. You can do this experiment in your lab with butane gas, so camping gas in the end. And my student Simon Krause at that time had the idea to film the sample and to check what is going on when you approach this very strange negative gas adsorption step. So he filmed the sample, and now you can see the sample is basically approaching this very strange negative gas adsorption step, and then suddenly what is happening is that there's gas coming out of the sample. So it comes out of the central part of the sample, and it lifts up the sample, so the powder starts to move, essentially. It's moving up. And then after the step, it's moving down again. And you see that it's even moving down deeper than it was located before. So with the naked eye, you can see that there's a huge structural transformation happening in this kind of porous material. And of course, the naked eye only shows you the powder, but to get an understanding what is happening inside the structure, you need X-ray diffraction, for example, powder X-ray diffraction. And we did this with the apparatus that we had developed at that time. And before this negative gas adsorption step, you have a large pore structure. Here is the octahedral pore inside. You have a cubic structure with about 100,000 cubic angstrom in pore size. But then suddenly when you approach this step, then the structure is contracting. So all the reflections are moving to higher angles, and this huge octahedral pore is contracted to be from 2.4 nanometer to less than 1 nanometer, essentially. And only when you dose more gas, when you increase the pressure further, then the structure is reopening again. And at the end, you have almost the same powder diffraction pattern than as compared to in the beginning. And also the unit cell size is almost 100,000 cubic angstrom again as in the beginning. Now, what is happening here to the structure? and to the biphenyl strut that is connecting the MOPs. The MOPs are not transforming, but the connections between the MOPs, the connections between these spheres are basically deformed. They are very severely deformed. You see, this is the biphenyl unit when it's very happy. This is the energetically favored form. But in this intermediate form, the biphenyl strut is very much deformed, tilted, buckled, basically. And only when the structure is reopening, again, you have the straight form again. So this buckling requires a lot of energy, basically. Here you can see also this kind of buckling and the transformation of the pores. This is the inner pore of 2.4 nanometer, which is then contracting into a 1 nanometer size pore, and the other pores are also contracting. Only the MOP pore is not contracting very much. So this is a self-contracting structure, and you're wondering why this is the case. Why should you contract yourself? Why should I pull myself together? But the reason is purely energetic. So when you calculate the energy for this is the open pore form, this is the contracted pore form. If there's no gas present, then the open pore form is the energetically favored form, basically here. And you don't want to contract because this biphenyl strut is very energetically deformed, basically, and this is not favorable. But when you increase the pressure, when you dose gas to it, there's an energetic gain because there's a higher adsorption enthalpy for the small pore as compared to a larger pore. And if this large pore of 2.4 nanometer is contracting to only 1 nanometer, there's an energetic gain. In other words, the methane feels more happy in a small pore, and this releases energy to the outside. And that's the driving force. This is the higher enthalpy, the higher adsorption enthalpy for the contracted pore phase. And this leads to a situation where essentially the contracted pore phase becomes more stable for an intermediate pressure. And only at high pressure, then there's so much methane that the best situation is to have a large pore, to absorb a lot of gas, basically. And then the sponge is really opening up again, and then the large pore form is the stable one again. So with this, we can understand also all the energetics behind this transformation. And nowadays, theory is so advanced. I'm always impressed by all the theoretical developments, and it's so valuable to cooperate with theoreticians to get a better understanding what is going on. And this was a cooperation with the group of Van Spijbroek and also Jack Evans, basically, in 2021. Nowadays, it's possible to screen the whole energetic landscape of these materials. So here on the y-axis, basically, we have the pressure, and on the x-axis, we have the cell volume. And you can calculate all the energetics. So blue, the deep blue, is the energetic minimum, basically. And the green, here it's green, and yellow, it's the very high energy areas, basically. And if you would only stay in the energetic minimum, you would go from the OP form. When you increase the pressure, so we start here, when you increase the pressure, we go to the CP form, here we have the contracted form, and then we would go to the OP form again. So this would be the equilibrium situation when you only go to the lowest energy. But reality does not always follow the equilibrium. That's also why we live, probably. If we would be in thermal equilibrium, then we would probably be dead. And so life is more exciting and interesting if there are barriers. And there are a lot of energetic barriers. If you want to swim here, and if you want to swim in the deepest ocean, you realize you have to go over a mountain here to come to the closed pore, to the contracted pore phase. And this is basically the reason that this structure is overloading itself. It's swallowing more methane than it can take up before it's contracting to the contracted pore phase, and then it's opening up again here. So these strange phenomena are purely kinetic phenomena, but this does not mean that you can wait longer and then you don't observe it. These barriers are so high that you will not experience them in your lifetime. I mean, you always have to increase the activation barrier. You have to increase the energy to go over the activation barrier, similar as in catalysis, because these are exponential functions. So again, you can also use in situ neutron powder diffraction. Here we localized all the methane molecules in the deuterated form inside the pores. And this was also quite interesting because what we realized is that when you enter this negative gas adsorption step, the small pores and also the intermediate pores are almost completely filled. But what is really starting to fill is this large mesopore. And this is probably one criterion also to find new negative gas adsorption materials is you have to have very large pores. So pores that are larger than 2 nanometer to find these kinetic barriers. And probably they are also associated with kinetic barriers of the fluid, not only of the solid. Now, of course, we are chemists. And now comes the rational. We are also trying to understand from a rational point of view how we can manipulate these phenomena, this negative gas adsorption. And so Simon Krause rationalized this basically with the energetics. And we just considered Euler's law here. Euler's law just considers the ligand here as a pillar, basically. So the question is, how strong does your pillar have to be to allow buckling, means crushing the column, or to sustain bending? And one important parameter here is the length of the column. The longer the column, the easier it breaks. And another important parameter is the elastic modulus. So in other words, the thicker the column, the more stable is your building. So if you want to make a rigid building, you have to have a very thick column. If you want to make a very fragile building, you have to make a very long and thin column. So we did this by chemistry. So we made all the different materials here with a small connection, a longer naphthalene connection, biphenyl, triphenyl, tetraphenyl. This material is interpenetrated, so it's a little bit different structure. But what you can see is basically for the small column, the very thin column, the short column, the material is rigid. You see no hysteresis basically in this case, but only when you have the biphenyl and the triphenyl, then you have the typical negative gas adsorption and the hysteresis. So in this sense, you can micro-engineer, you can rationalize basically how you can construct these type of materials. Up from a certain length, basically, on you will observe these breathing phenomena, these structural transformations, and then also negative gas adsorption. And then you can also follow this with in situ PXRD techniques. You can also tailor the elastic modulus, so in other words, the thickness of the column. So we also did this here. So we made this pyrene, this substituted linkers, also DOT-149, for example. This is still unpublished, but probably will come out very soon. And what we found here is that here you have the negative gas adsorption, but once you make it thicker, then you have the rigid behavior, no flexibility, basically. Here you have the flexibility phenomenon. Here it's a bit more complicated, but here you have also the rigidity. So by making the column a little bit thicker, you can also here tailor the behavior. This was here for the butane adsorption. So this was part of the ERC grant study that we followed for many, many years, and we summarized all our findings here in this review recently. If you're interested in it, please look at it. So I think there are still a lot of open questions because there are very few materials that show this counterintuitive phenomenon, and still a world to explore to find new materials that show also this negative gas adsorption phenomenon. So one of the take-home messages here I wanted to give is that there are many factors that are affecting the flexibility. And as an experimentalist, you have to be very careful, not only in the characterization, but also in the synthesis, the preparation, and how you handle all your materials. You can tailor the properties of your materials with the framework building blocks, the cluster, the linker, but also a very important parameter is the crystal size and morphology. And if you vary it at the same time, things become confusing. So you have to be very careful in this respect. There are also effects like the desolvation, how you desolvate your sample. The surface also plays a role, and I would also like to stress that often the sample history plays an important role. This is something that we often forget, that a material changes. It memorizes a lot of things that you have done to it. Similar to you, I mean, you also have a memory, and you experience something when you train, or you become stronger. If you don't train, you become weaker. So this is similar to these materials. When you do a characterization, then you also change the characteristics of these materials. And I also wanted to show that disorder also plays an important role in these kind of materials. And it's interesting also in the end to look at the history of the flexible metal organic frameworks. Of course, we are not the only group working in this field. Many people have contributed, like Babur, to the development of in situ techniques and new materials. Many people have also worked in the theory like Couder and Guillaume Morin. Here in Milano, there was a lot of very interesting studies on the dynamics of linkers, especially. This is an aspect that I've not talked about. And what is also quite interesting is to see that right after the first development of the MOF, the Metal Organic Framework 5, in 1999, the first flexible MOF was discovered, ELM11, in 2001. But at that time, also because the methods were not available to analyze the structure, people did not understand what was going on. They only observed the adsorption phenomena, the gating type of phenomena. And since then, this field has really developed quite broadly. The group in Ferret, in Versailles, Gérard Ferret, with the mill materials, we with the DUT8. ZIF8 is also a prominent material. The shape memory effect was discovered. Jeff Long discovered the efficient methane storage with the BDP type MOF, and then also our discoveries of the negative gas adsorption. And of course, this history also continues. I did not talk much about functions, but obviously there are many people who like to explore functions. These materials have ultra-high selectivity for gas separation, so many people are exploring that. But you can also use them for polymer separation. There are some specific polymers that only open the pores, while others are excluded. I talked about the hydrogen-deuterium separation. Jeff Long explored these materials for methane storage. They also have a very high methane storage capacity. But there are also very interesting applications in the field of sensing, because always when the structure is changing, you also have a change in the physical properties that you can use also for sensing. And last but not least, these materials are dynamic, like us. We are moving. So you can make these materials moving. And this has been also explored as actuators, for example, by the group of Maspoch, and also as shock absorbers. And these are also interesting fields that can develop in the future. With this, I would like to close and thank, of course, all my students. I have a great team. And also this study very much profited from great cooperation in theory and many measurement techniques. I'm very thankful for the ERC Advanced Grant and also from the DFG, who funded a research unit on this topic. And before I thank you for your kind attention, I would like to advertise a conference we are organizing on the characterization of porous solids in May next year. Dresden is also a beautiful historical city. I hope you will enjoy it if you have time to come. And we are also organizing a pre-conference for PhD students and postdocs to present their work there. So please submit your abstracts, and thank you very much for your attention.
Thank you very much for the beautiful presentation and so for about all your research that is really challenging and so full of characterization, details, and so in order to understand deeply what's going on, how these MOFs behave. And then it's open for questions. Okay. First of all, Professor Montalenti. He is a physicist.
Yes. So it was impressive how much effort you put into fine characterization and in trying to build a rationale of what's going on. Can you give an example, since these are materials that have applications, one example where, you know, it really paid off to spend so much time in characterizing, you know, small details than to have something functioning, for example,
So yes, of course, we had, of course, different approaches. So I think we, on the one hand side, we try to get a deep understanding by studying model systems. So these are certainly model systems that give you a deeper understanding how these materials work. I think for the main goals, these materials have very high selectivity in gas separation, especially when it comes to methane, CO2 separation, or also ethane-ethene separation, ethine separation. And this is probably not so much our work, but other people have shown that you can really reach a very high selectivity because these materials are responsive. They only open their pores for one species, so only one species is taken up, basically. And there are also very specific phenomena where we observe so-called inverse selectivity. That means that normally, for example, for ethane, ethene, the ethene has a higher adsorption enthalpy, so in a normal adsorbent, the ethene would be taken up preferably. But due to the induced fit effects, basically, in some of these flexible materials, we can observe also inverse selectivity, where the ethane has the higher uptake in this case. So in terms of commercialization of metal organic frameworks, we have to say that these materials are still at a very early start, these flexible materials. That has to do also with the lack of understanding. Also, there are also some intrinsic questions, because if you have a gas storage system and the MOF changes its shape, that it means also that the material basically expands and shrinks. And there are also fundamental questions associated with the question if this can be ever integrated in a storage system. But in terms of commercialization, the highest TRL has been achieved basically in the area of CO2 capture for metal organic frameworks. And this is the famous CALF-20 system by the Calgary group, basically, commercialized by Svante. And what we see currently is that most of the funds are basically in the area of CO2 capture. We have about 30 startups in the world in the metal organic framework, and some larger companies also working in this field still. And I would say 50% of these startups have funding in the area of CO2 capture. For example, Mosaic also is a company in the US. Whether this is a trend or a sustainable trend or not is always hard to say for the future, but at the moment this is a very important topic. In terms of smaller applications, I think the strength of the metal organic frameworks is also in air purification, because these materials can take, you know, we have a lot of pollutants in the air, for example, in cabin air and closed buildings also. And the MOFs can have sometimes advantages in taking up very small polar molecules, like, for example, formaldehyde, acetaldehyde, and so on, which are toxic compounds. And I think on the long term, we will probably also see some applications in this area. Yeah.
Thank you very much. Jacopo,
so, thank you for your very nice and very exciting presentation. And so I start from your presentation, actually. So based on your work, on your beautiful work that also you show here, and based also like work of, for example, of Mike Z and Professor Susumu Kitagawa on flexible materials. So how far do you think we are really to have the opportunity to really design from first principle flexible material with targeted properties? And how do you think also, like, for example, artificial intelligence and large language models, for example, can help us in this achievement, in this goal? So the true rational design of this material from first principle.
So I think the rational design is very far developed. So computer methods nowadays are very powerful. They are especially powerful in calculating thermodynamics, stability, and stability curves and uptake curves and so on. One lack of theory at the moment, I think, is still the kinetic barriers. So this is something, it's similar in catalysis. The transition state, to calculate the transition state, is much more demanding as just the starting and the end state, basically. And I think this is still an open field where more development is needed. And in that sense, having said that, I think that there's a huge power, especially in machine learning. I'm not sure if language models really help there. This is very popular, language models, but this is more our interface, I think. But I think the machine learning, predictive AI is very powerful in screening a lot of materials, basically, with their properties. But having said that, one should also realize that the machine learning always stays in a certain realm. You feel comfortable with a MOF, which has a perfect structure, and with a gas that has no bonding interactions, like methane. But when it comes, for example, to a very simple molecule like water, which can make some strange hydrogen bridges or dissociate or make some bondings to a cluster, then the methods are not fast enough for screening. So I think these are the main challenges to go also for real applications, because water is everywhere. I think this answers also a little bit your question. For the CALF-20, for example, it was decisive to find that the CO2 has a higher affinity to this material than water. And this is almost not predictable. And I've seen also prediction of water isotherms which are far away from reality. And I think this is still something that we need to develop further. But I'm also an advocate of putting more data online. And I didn't show a slide on this, but we have also developed an initiative where you can basically deposit all your adsorption data as digital formats. We call this the Adsorption Information File, AIF. And I think this will also help the people who do machine learning to have more data, precise data available to develop more machine learning tools. So I think the forefront is really kinetics, to predict kinetics of materials, and this is here of utmost importance, and also to develop more rapid methods that also include chemical reactions. I think that's also the challenge. Yeah.
Okay, questions? She's Professor Livia Giordano. She's a physicist, but she has been working in the field of electrical calculations.
So thank you for your very nice presentation and for showing such a beautiful experiment. And so my question is about the stability of these materials. So how sensitive they are, for instance, to the atmosphere they are exposed to, for instance, the relative humidity, the presence of water, or the temperature.
So, thank you for this question. So these materials are relatively stable when they are solvated, when you have a solvent inside. So after the synthesis, for example, or you can solvate them with a certain molecule, then you can handle them easily on the lab bench. But once you remove the solvent, they become responsive. They absorb everything. And of course, the first thing they absorb is the water from the atmosphere. And in these materials, this can be very critical. And these materials are not made for water absorption, but there are other materials that are very good for water absorption. There are even companies commercializing MOFs for water absorption to harvest water in the desert, for example. And the most prominent ones are based on aluminum or zirconium-based MOFs. And these materials are sometimes also responsive, but they are sometimes also just rigid metal organic frameworks. And they can absorb water reversibly many, many times. We also published one material, DUT67, a zirconium MOF, with very high ability to absorb water. And this also has gained attractive applications, basically, on the one hand side in the area of humidity management. So if you want to, for example, here in air conditioning, you have to extract, if you cool, you also have to basically take the water out. This is the biggest energy consumer in this process also. And at the same time, you can also use the water adsorption for heat management because the adsorption, the material is getting hot, and when you desorb, it's getting cold. So you can also use this for cooling applications, for example. So the materials that I presented are not for water adsorption, but there are a lot of MOFs that are also available for this kind of application. Yeah.
Okay. Questions? So, here.
In the case of two gases entering the same systems, like CO2 and methane, can you distinguish the environment by the chemical shift? For example, for ring currents and with the aromatic rings. I've not understood the details. So.
Yeah, so this is a bit a complicated question. So, but in the example that I demonstrated, so we have both gases in the gas phase, but only one gas is adsorbing in this case. So that's maybe a different situation here. But here it's not so much the ring current that is affecting the chemical shift, but it's more the limited degree of rotation, basically. The CO2, in this case, the CO2 is very much aligning inside the pore, and therefore in the static NMR experiment, it develops this tensor here, basically. So this is a very broad tensorial signal, while the signal in the gas phase is very narrow. And here we have both gases in the gas phase, but we don't detect any, there's no methane in the pore, basically. So we in this case, we don't detect it at the same time. Yeah. So it's not, in this case, it's not present in the pore at the same time. Yeah. Yeah. Yeah, beautiful anisotropy, yes, yeah.
So,
Thank you for your presentation. I want to ask only about the first example you showed, the DUT-8, when you showed the absorption of the nickel example. How do you obtain the two forms? The closed one and the open one, which triggered the transformation between the two? Is the temperature, because you show gas absorption for the two different forms.
You mean these different forms, right?
Yeah, you showed that.
Yeah.
How do you prepare the two forms?
Yeah, this is basically by synthesis, yeah. So we have different synthesis recipes, basically. Here we get very large crystals, here we get small crystals. So in the synthesis, what you often do is if you have a very high supersaturation, then the nucleus in the synthesis becomes very small and very many at the same time. And this allows you to make nanoparticles, basically. So in this case, we use an excess of the DAPCO for the synthesis, because this way you deprotonate the carboxylic acid and you get a very rapid precipitation, basically. And that's the trigger to make the nanocrystals. And in the beginning, we were also not so sure what's the reason, or if there's like a different amount of DAPCO inside or something like this. But at least based on our methods, we checked elemental analysis and NMR and so on, and they have all the same composition, but they show completely different isotherms. So this one is basically a pure rigid one, and only the large crystals basically show the responsivity in this case, and only they show the pore opening and the pore closing. So we always have the open form when we have the solvated case, basically. Or maybe I misunderstood your question. So,
Because if I remember the one
Yeah. Yeah, this is. Yeah, basically by particle size. So these are just different particle sizes. Here we have the closed pore form in the beginning, and then when we have the gas uptake, we go to the open pore form, and then in the desorption, here we still have the open pore form, and then here we close. And these hysteresis you only observe for large crystals. And if you synthesize your material as very small nanoparticles, then after the solvent removal, your material stays in the open pore form, basically. So while for the large crystals, you go to the contracted pore form, basically. So in essence, they show different desolvation behavior. This one stays in the open pore form, and this is actually also a metastable form in the end. Because from thermodynamics, it wants to contract, but because of the higher surface energy, it stays in the open pore form. Actually, when you heat these crystals to higher temperature, they also start to contract. So at 200 degrees centigrade or something like this, they also start to contract. But there's also some sort of decomposition, or there's also some rearrangement. We find also a different form. Therefore, this can be not used to make the CP small particles. But when you desolvate it, you end up in a metastable open pore form. And here you see this open pore form basically because this material takes up the gas immediately from the beginning. And also there's no hysteresis at all, so that's the characteristic. And we find this as a general phenomenon. Often, when we make nanoparticles, the material becomes rigid. While if we have big particles, the material is flexible. There are also a few rare cases where it's the other way around, that the material becomes flexible when it's small particles, but in many cases it's the other way around. This depends on the energetics of the material.
Any question? I have one. So when you showed the last example, then the pi-phenyl can be flexed, can be bent, let's say. What about the terphenyl? Do you think that the terphenyl can be more bended? Have you tried it? Because so I was thinking if. Okay. Yes, exactly. Yeah. Beautiful. And so, do you think that it becomes? It can be bent a little, too? Okay.
Also shows the it also shows the transformation. When you look into the XRD, what you also see is that you see the peaks of the contracted phase, but you still also see some peaks of the open pore phase. And I think these transformations become less distinct, or the material, because the material in general becomes more flexible, more soft. So you also see a trend towards amorphization at a certain point, basically. If your material becomes too soft overall, then you don't get a clear transformation between OP and CP form. But yes, this also buckles. It also shows the buckling. Yeah.
Regarding the example of the DUT8 with the nickel, when you showed all the disorder structures about the nodes, let's say, yes. What about instead the naphthalene unit? Was it dynamic? Was there dynamics inside the ligand, the organic ligand?
So we looked into this also. I don't have a slide here. We looked into this also with dynamic NMR spectroscopy and the deuterated linker. But according to our observations, let me see. I think it's somewhere here, maybe. Sorry for this. It's here. Here, right? Yeah. So I think this was also my theory in the beginning, that the whole system is dynamic and that the linker is always rotating. But the NMR results show that this is not the case. So it's always a stepwise transformation once you change the solvent. But there's a small flip movement, but there's not a continuous rotation. Yeah. It would be also very interesting. I mean, this is maybe also something to think about. to couple the rotation with the structural transitions. That would be also very interesting to get a deeper understanding, I think, and could be quite fascinating. And there are some cases where people have substituted, the group of Roland Fischer, they have substituted a lot of organic groups here on the side, and this induces more entropy, basically, so there's more energy with the rotation. And then they see also some thermal transitions in this case, but in this case, there's no continuous rotation.
Thank you very much. So, if there are no questions, I would like to thank again Professor Kaskel. And so thank you for your participation.